Good afternoon everyone, and welcome to today's worked exam answer video. Today I am having a look at a bit of a hybrid organic synthesis / NMR multiple choice question, and the reason why this particular question is a hybrid of those two things is because we have to use the reagents and conditions provided to first of all work out the products of those reactions, and then once we've determined what the organic product for each reaction is, we then have to find the one that only gives us 2 peaks in its proton NMR spectrum. So this is a very demanding question, and it's expecting us to know a lot of different organic reactions, but then also in addition to that understand proton NMR, and that's why I've chosen to do this question. Now, I think for yourselves the best way to do this is to draw out the organic product of A, B, C and D, and then once you've figured out which would only have 2 peaks in its proton NMR spectrum, you can stop. Myself, with a bit more experience, might be able to have a look through the options and think, I definitely know that that's either going to have fewer than 2 peaks or more than 2 peaks, but that is me using my experience and also relying on my ability to visualise what things look like in my head. So for now, I would suggest drawing out the organic products, and that's exactly what I'm going to do here so that you can see well, first of all, what the organic products are, and then how we can tell for those products how many peaks in the proton NMR spectrum we will have. So when we're thinking about 2 peaks in the proton NMR spectrum, first of all, we need to be thinking that that means that there's only 2 hydrogen environments, because the number of peaks that we see is dictated by how many hydrogen environments there are. So that doesn't mean that there's only 2 hydrogen atoms, it just means that of all the hydrogen atoms we have, some of them will be in one particular environment and then the rest will have to be in that second environment, and we can't have fewer than 2 environments and we can't have more than 2 environments if we want to only see 2 peaks. So that's, I guess, the first thing that I will note down. Now, like I say, what I'm going to do is for each reaction is I'm going to draw what is going to be formed in that reaction. So this is where my overall organic knowledge will come in, because yes, these are sort of individual reactions that we need to be aware of, but these are covering all sorts of reactions from both year 12 and year 13 from across the spec. So we do need to have our knowledge of all the organic reactions kind of nailed down for questions such as this, just like we would in organic synthesis. So we've got butantuol, which is an alcohol, it's a secondary alcohol, and we've got acidified potassium dichromate. That is the oxidizing agent that we use to oxidize primary and secondary alcohols, and because it's a secondary alcohol, we're going to get oxidation to a ketone. So I'm just going to make those notes here. So it's a secondary alcohol plus my oxidizing agent, therefore we're going to get a ketone, specifically butanone, so 4 carbons, and then on one of the 2 middle carbons we will have our double bond O, and it doesn't matter which one because it depends on which side we count from. I tend to count from left to right if I have a choice, so I'm going to put the double bond there. So that is the first step for part A. We've now got our organic product. We would also make water. That's not an organic product because it doesn't contain carbon. So in terms of how many hydrogen environments we have here, we're going to have too many. And I'm just going to grab some different colours so that we can, or I can, show you where those environments would be. So we would have these 3 hydrogens there. They would be in one environment. They would be in a different environment from the H's on the other end, because although the 4th bond of each of them carbons is to another carbon, one of those carbons has the double bond O and the other has two hydrogens. So they are different environments. There'd be different carbon environments and the different hydrogen environments as well. And then we'd have these hydrogens here that would be in their own environment. So the answer is not going to be A, because we have 3 environments, not 2. Okay, moving on to the next example. We've got B, and B is telling us that we've got ethanol chloride, which is an acyl chloride and an alcohol. So an acyl chloride and an alcohol, we're thinking about nucleophilic addition elimination. The oxygen of the OH of the methanol will be the nucleophile, will attack the delta positive carbon of the C double bond O in the acyl chloride, and that will therefore give us a C double bond O next to an O, so that's going to give us an ester. So we're going to have the 2 C's that we had on the acyl chloride with the C double bond O, which reforms in the elimination step of the nucleophilic addition elimination. Then the Cl will get kicked off of there, and that will then become the O of the methanol, and then we're going to have a CH3 there. The other product would be HCl, hydrogen chloride, because the H of the OH of the alcohol group goes and the chlorine of the acyl chloride group goes, but again, that's not our organic product. That is our organic product, and hopefully at this point we're thinking, this could be our answer. Only 2 peaks in the proton NMR spectrum, only 2 hydrogen environments, and I think that's exactly what we've got. So we've got the H's over here, and again, they are not the same as the hydrogens on the other side. And the reason why they're not the same, again, all 3 hydrogens are on a carbon, but these hydrogens are then not bonded to a carbon that's then adjacent to another one, because we've got the O of the ester linkage there. These H's are on a carbon that is bonded to another C, so the atom next door, not the same. So we can't always just see 3 hydrogens on a carbon and think, oh yeah, same, because usually they won't be. And there's no plane of symmetry, and identifying planes of symmetry is a really good way to know whether we've got hydrogens that would be in the same environment, and same for carbon atoms as well. So I think that this should hopefully be our answer, because it has 2 environments, and because it's multiple choice, we hopefully won't find another that has 2 environments. So let's go with the answer being B, but I will work through the others to show you why they are not the correct answers. So thinking about C. C says we've got propanoic acid, so a carboxylic acid and ethanol in the presence of concentrated sulfuric acid, which is going to be our catalyst. Carboxylic acid and an alcohol, we're going to be making an ester. And the concentrated sulfuric acid is a nice clue there, because yeah, they'll always mention that if we're doing esterification, and we don't use concentrated sulfuric acid very often as a catalyst, so that is one of our nice clues. So when we make an ester, it's the carboxylic acid that kind of comes first. So we've got propanoic, so 1, 2, 3. The C double bond O of the original carboxylic acid stays, but then the OH of the propanoic acid comes off. The H of the ethanol is going to come off, and then the O of the ethanol goes there to give us our ester linkage, and then we would have the 2 C's of the ethanol. Just like that. The second product would be water. Again, that's not the organic product because it doesn't contain carbon. So in terms of our hydrogen environments, I can see why they've put this in as an example, because again, there would be potentially some students that would think that these 2 CH2 groups that those hydrogens would be in the same environment, and that these three on this CH3 and these three on this CH3 again would be in the same environment. They're not, because there's no plane of symmetry down the middle here. These hydrogens are on a carbon directly adjacent to the oxygen, these ones not adjacent to an oxygen, and because this CH2 group is different from this one, that means that these CH3s will also be different. So in this instance, we are going to have 4 hydrogen environments, but I can see why they've included that as an example, because some people would be unsure as to whether we had the CH2s being in the same environment and the CH3s being in the same environment. But we do not, because for them to be in the same environment, we have to have the exact same bonds, and we should continue working our way throughout the molecule until we get to a difference. And it's only if we don't get to a difference that we would then be able to put 2 atoms in the same environment. Oops. Bit of a faux pas there, I've used the green twice, my apologies. Let me go over that and make it a hideous looking brown. You'd think I'd be alright at this whole speaking and writing at the same time thing about now, but clearly not. So there are 4 environments in this one, 4 hydrogen environments in this one. So that is a no. Thankfully, because we were hoping it was going to be a no, because we think we've got the right answer already. And then finally, we've got to think about ethene reacting with hydrogen in the presence of nickel. So if we've got H2 and Ni as our catalyst, we should be thinking about breaking double bonds, in this case, because it's an alkene. So we're thinking hydrogenation, so we're going to get an alkane. So the alkane that we're going to get if we start with ethene will be ethane. There we go. And with this one, we only have 1 hydrogen environment, because we do have a plane of symmetry smack down the middle between the carbons. So actually all of these hydrogens would be in the same environment. So we've only got 1 environment, so we'd only have 1 peak in the proton NMR spectrum, which again is not what this question was looking for. Therefore that is also incorrect, and therefore thankfully B, the only one with 2 environments, therefore that has to be our correct answer. Now, like I said at the start, hopefully you will get to a point with these questions whereby knowing the products of these reactions comes fairly quickly, but also as soon as you're thinking butan-2-ol turning into a ketone, that you can start to picture this in your head and therefore go, not symmetrical, so 3 environments, not that one. Obviously, if you work through them in order, you'd get to B, hopefully identify that there's 2 environments and then stop because you've got the answer. But again, it's about knowing all of these reactions and thinking, okay, propanoic acid and ethanol, when I'm going to have 2 carbons before the C-double bond O with hydrogens, and then I'm going to have 2 carbons on the other side of the ester with hydrogens, and they're going to be in different environments, so it can't be that one. The first one I immediately clocked onto when I looked through these is D. Knowing we had ethene and that I was opening up the double bond, I knew that we were going to have only 1 environment because of all the hydrogens being in the same environment, as we had that plane of symmetry down the middle. So D was the one that I ruled out straight away when I had a look at these. Then A. B took not longer, but I kind of then just went to the beginning. And B, I think because it's a trickier mechanism, it just took a minute to think about what product we were going to make. But yeah, the better you get at that in terms of knowing what products you're going to make, being able to visualize what the product's going to be like, the quicker this would be. Now, of course, you wouldn't have to draw this out nice and neatly. You wouldn't have to, in A, go around all the different hydrogen environments or anything like that. Quick sketch at 2 environments, brilliant, got the answer, move on. Or not 2 environments, okay, what's the next one? But yeah, the speed at which you can come to these organic products is going to be quite important in how long this question might take. But hopefully that all makes sense. Hopefully in terms of the environments for the hydrogens, it makes sense, as I was explaining, in terms of the lack of completely identical bonds where we don't have the same environment, but then exactly the same bonds here because of the planar symmetry where we do have only one environment. Any questions at all, as always, please do not hesitate to ask. You can leave a comment on the video, you can send me a DM on TikTok or Instagram, or drop me a message on my Facebook page, or you can send me an email to missgtutoringandresources@outlook.com. Thanks so much for watching, guys, and I hope you have a really wonderful weekend.